Hello everyone. This is going to be the solutions key to the WebAssign that was given for week 3 online for AP Physics C. After this week, we are going to move into review for the AP exam, as was definitely the big request. Since I already have this module out and about, I'm going to finish off the magnetic forces portion of it. So we'll continue doing this for this week, but then as soon as we come back from spring break, we will be going full force into review. So the first question talks about a charge going into a magnetic field, and we are given some information about it, and it's asking us what is the sign of the particle and what is the mass of the particle. So in this particular case, the summation of forces equals mass times acceleration, but the acceleration is going to be circular acceleration. It doesn't actually speed up the particle. All it does is change its direction. Now you'll notice on the left side of this equation I've done a QVB sine theta. That's because that is the magnetic force acting on the charge, and that's the only force acting on the charge. People often ask, well, isn't there gravity? The answer is yes, there is. But the gravitational force is so incredibly small compared to this magnetic force that we neglect it. It's sort of like throwing a $5 bill at a multi-billionaire. I mean, yes, they are $5 richer, but nobody really notices that. So our goal here is to solve for the mass, and we see mass on the right side. So let's move R and V over to the left, and now we can solve directly for the mass. I do keep in mind they do want it in astronomical, or not astronomical units, atomic mass units. So we're going to take the final mass and we'll divide it by 1.66 times 10 to the negative 27th. So here we go. 3.2 e negative 19. The b value is 0.16. The r value is 1.013 meters. We have to convert the centimeters to meters. And the velocity 1.2 e6. We go ahead and we punch all of that happy fun stuff into a calculator. Upon doing so, I end up with 4.32 e negative 27. So what I would do is my final step again right here, 4.32 e negative 27. I'm going to divide that by 1.66 e negative 27. They're both e negative 27, so effectively it's 4.32 divided by 1.66. And I got 2.60. So 2.60. Is it positive or is it negative? So what I'm going to do is I'm looking at my computer screen. I see dots from the magnetic field. So I am holding my right hand so my palm is facing my face as I am assembling the FBI gun law. So I am looking directly at my palm based on the magnetic field, because the magnetic field should be coming out of my screen, so my palm should be facing me. My index finger points up, and my thumb is to the right. Now, this tells me that if the charge is positive, it would go to the right. And according to the diagram, it does. So that tells me this has got to be a positive charge, 2.60. Now, let's say this particle is actually going to the left, even though the FBI gun law said it should go to the right. Well, that just tells you that the particle is negative and not positive. Let's take a look at the next one. This is similar to what you did last week. I will delete this and pop this one in. We have two long straight wires carrying current. So here's wire 1, here's wire 2. Their separation is 20 centimeters or 0.2 meters, 70 amps, 70 amps. The magnetic field created by a wire is mu naught over 2 pi times I over R. So let's focus on this wire right here. We'll call it the blue wire. The blue wire, I don't care about direction right now. I'll deal with direction in a moment. The blue wire creates a magnetic field that is equal to mu naught over 2 pi. Actually, what I'm going to do is anything that is a constant independent of the wire, I'm just going to leave it black. So mu naught over 2 pi times I over R. So R is 0.20, and I have the 70 amps from the blue wire. Now that's the magnetic force, the magnetic field created by the blue wire. Let's call this one the red wire. The magnetic force that the red wire experiences, rather force per meter, is Bison. The sine of theta is going to be 90 degrees, so we can just call that a 1. Let's go ahead and put in information that we know about. So force per meter is equal to the current on the red wire, which is 70, times the field strength from the blue wire, which is mu naught over 2 pi times 70 over 0.2. Once again, this equation is showing you it didn't matter whether you found the red field exerted on the blue wire or the blue field exerted on the red wire. It will be the same. Newton's third law would confirm that for us as well. Newton's third law will confirm this for us because, well, when object A exerts a force onto object B exerts the same magnitude of force back onto A, but just in opposite directions. After some happy fun calculations, I got 0.0245 newtons per meter. Let's go ahead back into WebAssign, 0.0245, and check that one out. And it's wrong. So I apologize really quick. I figured out what I did. It should not be 0.0245. It should be 0.0049. What had happened is I punched it wrong into my calculator, so I paused the video really quick and updated. And there we go. I accidentally squared the 0.2 in my calculator, but everything you see here is correct. It was just an error with the calculator, that's all. Does the force pull the wires together, push them apart? And alright, so we are told that the current is flowing in the same direction. So we'll say the blue current is flowing upwards, which means according to the right-hand rule, we have a magnetic field from the blue wire that looks like this. According to the FBI gun law, I would, for the red wire, have my palm facing the computer screen this time as opposed to my face, my index finger pointing up, and I see that my right thumb is pointing to the left or towards the blue wire, which means the blue wire would have a force in the opposite direction, or directed to the right, or directed towards the red wire. So they are pulled together, and if the current flows in opposite directions, that's actually what would push them apart. So double check and success. Alright, we're down to 1. Number 3. So in this case we have a wire which has a current I1 of 18 amps and a loop of wire current I2 of 30 amps. And the question is, well, what kind of force does the long straight wire at the top exert onto the loop of wire? We're going to use what we just did. The force between any two wires is mu naught over 2 pi times I1, I2 over R. I have shown how this equation is formed in the bonus question last week, and I just showed you in question 2. So no, this is not on your equation sheet, and yes, I am jumping right into it in the interest of time because we've already derived this twice now. But what I'm going to have to do is I do know that the top wire here, top part of the loop, is going to be attracted, and the bottom part is going to be repelled. If you remember in the last question, when the currents were flowing in the same direction, they were attracted. And they're flowing in the opposite direction, they were repelled, which means that I said that backwards. This top wire will be repelled, and the bottom wire will be attracted. So my apologies for that. All right, so let's figure out, well, what is the force on the top wire? If you haven't caught on to it, mu naught over 2 pi is 2e negative 7. And you say, well, why not just make it 2e negative 7? That has to do with mu naught being the fundamental constant. It's how the magnetic field moves through a vacuum. That will change in future problems if we get there in magnetism. 18 and 30 are my currents. Sorry, I forgot to put, this is force per meter in this wire. So what I'm going to have to do is move the L to this side, because I do actually have a length of the wire, and the length of my wire is 39 centimeters, so 0.39, and then the separation between the top wire and the top of the loop is 0.065. Alright, now I'll punch this in. 2e negative 7 times 18 times 30 times 0.39 divided by 0.065. The verdict is 6.48 e negative 4. The force on the bottom, same equation. The only thing that's going to change is the separation distance. Instead of being 6.5 centimeters, it will be 6.5 centimeters plus the additional 13 centimeters, bringing it up to be 19.5 centimeters, or 0.195. And the result here is 2.16 e negative 4. All right, so let's sum up those forces. The top wire has a force going downwards, so I'll put negative 6.48 e negative 4. And the bottom wire has a force going upwards, so positive 2.16 e negative 4. The verdict on this will be a negative 4.32 e negative 4 newtons. The negative indicates down. So as I type this in, I'll go 4.32 e negative 4 newtons. Magnitude stays positive, but it's going down or away from the wire for the direction. And we have victory. Let me know if you have any questions. Enjoy.